Okay, so I'm starting to get the hang of this, I think. So, okay, so in a previous lecture, I'd asked you to look at this relationship. Let me just get my laser pointer. I'd asked you to look at this relationship here, which is, just a constant times e to the I a x plus a constant times e to the I bx plus a constant times e to the I cx. And those constants are meant to be, they're meant to be capital A and lowercase a, capital B and lowercase b, and capital C and lowercase c. And then I wanted you to show that if that relationship held for all x, then the capital A plus capital B has to equal capital C, and lowercase a has to equal lowercase b has to equal lowercase c. And so the first one of this is really trivial. Let me just do my display here. So I'm going to do this. You're right. So the first one of these, the one that's here, a plus b equals c, is trivial because if I just set x equals 0, then what I'm left with, e to the I ax is equal to 1, e to the I bx is equal to 1, and e to the I cx is equal to 1. And so I have a plus b equals c. And then if that's for x equals 0. And so that first one is obviously, that has to hold if this is true for all x. And then what I do is I take this equation and divide it by e to the I lowercase cx. And so I have a e to the I a minus cx plus b e to the I b minus c times x equals capital C. And I take the imaginary part of that, which is a sine a minus c times x plus b sine b minus c times x, and that equals 0 because the imaginary part of c is 0. And so if I and here I'm going to make a statement here, and I'm going to ask you to think about it because it has to be true, and it's and I just like you to kind of imagine that if a minus c is, so if a does not equal c, and if b does not equal c, so we have these two sinusoids with different constants multiplied by x, okay? And I'm going to say there will be places on the x-axis where both of these two terms are positive, right? And that, like, if this number a minus c is not the same as this number b minus c, that statement will be true. And if both terms are positive, this cannot be true. Okay, so that means that a minus c has got to be equal to b minus c, and a minus c has got to be equal to 0, and b minus c has got to be equal to 0. And there are two special cases that one has to think about with this, and that is if a minus c is 0, if a equals c, well then b minus c has to be equal to 0, or this will be non-zero sometimes, and vice versa. And so it has to be true that lowercase a equals lowercase b equals lowercase c. And you'll see why this matters in just a minute. It's a very, very important thing and good thing to remember that this relationship holds. It's a question in Griffiths to show this, but anyway. So this material we're going to be talking about today for the rest of the lecture, and I'm sorry again, I should have had this up yesterday, but this has been going slowly. I also got vaccinated yesterday, which kind of knocked me off my feet, but I'm feeling good about that. And so we're doing section 9.3.2 and section 9.3.3 in Griffiths today. The idea here in 9.3.2 is I have an electromagnetic wave with a k vector, which is in the z hat direction. And I've got an interface between two materials, which is the z equals 0 plane. And so this electromagnetic wave is normally incident, or incident normally, on the interface between two different materials. And I'm going to say I have an incident wave, I have a reflected wave, and I have a transmitted wave. And I'm going to say that I'm free to specify what the incident wave is. And so the incident wave is E naught e to the I k1z minus omega t times x hat. So I'm saying it's polarized in the x hat direction. So it's a linearly polarized wave. And then if that is the incident wave, then the incident magnetic field is equal to E naught over V1 e to the I K1Z minus omega t times y hat. And again, y hat is k hat cross n hat, where n hat is the polarization vector of this incident electric field, electric part of the electromagnetic wave. Okay, so that's the incident wave. And also I would say that the reflected wave k vector is equal to k1 minus k1 times z hat, and the transmitted wave vector is equal to k2 times z hat. And you'll note I'm using the constant k1 for both of these k vectors and a different constant k2 for the transmitted wave vector. And that's because we will come back to this, but this makes sense, right? Because I know, and we're going to show this, but I know the frequency of the incident and the reflected and the transmitted waves are all, the frequencies of those three waves are all the same. And then the k vector, which is determined by the wavelength, and the wavelength is determined by the frequency and the wave speed. And the wave speed is the same for the incident and reflected wave, because that's just the wave speed in this material. And then the wave speed of the transmitted wave is different. And so I have a different k vector, different wave number for the transmitted versus the reflected and incident waves. Okay, so if I specify this incident wave the way I've specified it, I'm going to say something rather general for the reflected and the transmitted waves. And that is, I'm going to assume in the book, he assumes that the transmitted and the reflected waves have the same polarization as the incident wave. That is, that the electric fields are all in the x direction. And then he goes through and works out what he works out. And then he asks in a question to say, well, you know, do we know that that's true? And then he says, so just assume a general polarization of the reflected and the transmitted waves, and then show that that polarization has to be that the waves, electric fields, are in the x hat direction, okay, or minus x hat direction, depending. Okay, so we have, when we do this, then my n hat vector, I'm going to say, is cos theta r times x hat plus sine theta r times y hat for the reflected wave electric field. So I've got ER is ER, the reflected wave, is equal to the magnitude ER times e to the I times minus K1Z minus omega t. And again, that's the form of a wave moving in the negative Z direction, times this general polarization, like this polarization vector, which is in some direction relative to the x hat direction. And then I take that and say, well, then I take my magnetic field, which I get as k hat cross ER divided by V1. And this is what I get here, ER over V1, e to the I minus K1Z minus omega t times minus cos theta R y hat plus sine theta R x hat. And I've just made this little notation here. And then the transmitted wave, again, it's just E transmitted times this exponential times this different n hat vector. And then my magnetic field, the transmitted magnetic field, is k hat for the transmitted wave cross E transmitted divided by V2. So that's ET over V2 times the exponential cos theta t y hat minus sine theta t x hat. And note that this is K2, that's K1, and that's K1. Now, note I've not said that it is e to the I. When I first did this, I remember thinking, why don't we just make this e to the I K1Z plus omega t, which is a more standard way of writing a left moving wave, or a wave moving in the minus Z direction. But there's a reason for that. And what it means is that at Z equals 0, what I want to do is factor out and not worry about e to the I times minus omega t. And so if I write it this way, then I've got an e to the minus I omega t in all 6 of these terms. And that e to the minus I omega t factors out, which is helpful. And so that's why you write it that way. Okay, and then note also, I have presumed that the frequency is the same for all 3 waves. We all know this is true, right? We know that that the frequency of the incident, reflected, and transmitted waves are the same. But why? Okay, I mean, it makes sense, but things have to do more than make sense. And so imagine if I have K incident, K reflected, and K transmitted, omega incident, omega reflected, and omega transmitted. So I have 3 different wave vectors, 3 different frequencies. Okay, and I'm again talking about normally incident. So all of these 3 wave vectors are in the direction of plus or minus z hat. Okay, but the boundary conditions at z equals 0. And so what we're going to be doing is we're going to be matching the electric fields and the magnetic fields according to the boundary conditions for the interface between 2 materials. And those boundary conditions they all will look like this. At z equals 0, the ikz is equal to 0. And what we have is some constant, which is related to the electric and magnetic field, some constant times e to the minus I omega incident t plus some constant e to the minus I omega reflected t equals some other constant times e to the minus I omega transmitted t. But that relationship that we did with that a plus b plus c thing earlier, what that tells me is that if this is true, for this to be true, and it has to be true, then omega I has to equal omega r has to equal omega t. So that means the frequency at all 3 are the same. Okay, and then since the frequency is the same, I've got omega over k is equal to v, and that means k incident equals k reflected equals omega over v1 equals k1. And I've got k transmitted equals omega over v2 equals k2. And so that's why I can write these down in this form with the omegas being the same for all 6 of these. I've got k1 on the left side of the boundary, and I've got k2 on the right side of the boundary. And k1 and k2, the wave numbers, are determined by the properties of the material, because the properties of the material determine the wave speed in that media. Okay. So at z equals 0, the waves have to satisfy the boundary conditions. Okay, and we have 4 boundary conditions. We have 2 boundary conditions for E perp and B perp. Well, 1 for E perp and 1 for B perp. But E perp and B perp are both equal to 0 because these are transverse waves. So that means that those boundary conditions are trivially satisfied because there's no free charge. So when I look at the displacement perp on one side minus the displacement perp on the other side, there's no free charge. So sigma f on the boundary is 0, right? And that means that and b perp on one side is equal to b perp on the other because div b is equal to 0. And that means that those 2 boundary conditions are satisfied automatically. All right. So we don't get any information from them, but they are satisfied, which is good. All right. So now what I'm going to do is look at z equals 0 at the boundary, k times z equals 0. And that, again, is the reason for writing that minus kz minus omega t for the reflected wave. I can factor out the e to the minus I omega t from all 3 terms. And then I have a boundary condition for the parallel component of the electric field. And that boundary condition, you'll remember, is the electric field in material 1, just on one side of the boundary, is the same as the electric field in medium 2 on the other side of the boundary. And so the x component of that, if I look back to these electric fields for the incident, reflected, and transmitted waves, then the x component of that boundary condition is E incident plus cos theta reflected E reflected equals cos theta transmitted E transmitted. And the y component from that is sine theta r ER equals sine theta t ET. It's simple to write down, and we've got that. And so that's one set of boundary conditions, one boundary condition. Okay, and then I'm going to look at the parallel component of the magnetic field, and the boundary condition we have, when from what we worked out before, is H1 parallel minus H2 parallel is equal to the free surface current density cross n hat, where n hat is z hat. Okay, and that is zero because there's no free charges in this situation, and so that tells me that H1 parallel is equal to H2 parallel. There should be a vector over that. Sorry. And that tells me that B1 parallel over mu1 is equal to B2 parallel over mu2. And I think I can actually put I feel like I'm actually joining the 20th century here, 21st century here, actually. So what I've got is then B1, H1 parallel is B1 parallel over mu1, and H2 parallel is B2 parallel over mu2. And that means that I've got these two quantities are equal to each other. And then I've got an X component from my formulation of the incident, reflected, and transmitted waves, which is ER over mu1 V1 sine theta R equals minus ET over mu2 V2 sine theta T, and EI over mu1 V1 minus ER over mu1 V1 cos theta R is equal to ET over mu2 V2 times cos theta T. So that's my boundary condition for my magnetic field, the parallel component of the magnetic field at the boundary. So the Y component of the electric field boundary condition gives me sine theta R ER equals sine theta T ET. The X component of the magnetic field boundary condition gives me sine theta R over mu1 V1 ER equals minus sine theta T over mu2 V2 ET. And so I want to rearrange that, take those two equations, and I get sine theta R times 1 plus mu2 V2 over mu1 V1 is equal to 0. And what that tells me then is that sine theta R is equal to 0. Okay. And then from the Y component of the electric field boundary condition, I have sine theta R ER is equal to sine theta T ET, but sine theta R is equal to 0. So that tells me that sine theta T is equal to 0. And so what this means is that theta R and theta T are either 0 or pi or 2 pi or 3 pi or whatever, right? But they're an integer multiple of pi, right? So because the sine of both of those angles is 0. Now, this means that cos theta R is plus or minus 1 and cos theta T is plus or minus 1. And we can pick cos theta R equals cos theta T equals 1, or theta R equals 0, theta T equals 0. And I've just asked, maybe take a minute while you're watching this and think about why I have the freedom to pick that. And just think about that for a minute. But ultimately, I'm going to go back a little bit. I know this is probably a little bit annoying when I skip through like this, but I'm going to go back a little bit and say that what this really amounts to, if I say, so these terms in ER, BR, ET, and BT, those terms, the sine theta R times Y hat, sine theta R times X hat, sine theta T times Y hat, sine theta T times X hat, all four of those terms are 0. And these terms are all 1 minus what, X hat minus Y hat, X hat, Y hat, okay? And if I picked it so that cos theta R was minus 1, all that would do when I worked through my math was flip the sign of ER when I get to where I'm going to ultimately get to, okay? And so the boundary conditions are determined by the physics, and I can pick that cos theta R equals 1 because all I'm doing is leaving whatever ambiguity of that 1 or plus or minus 1 in this constant out front here, which I don't know what it is anyway, right? So it's plus 7, minus 7, I don't know, okay? So I hope that makes sense. So it's because we can put cos theta R equals minus 1, for example, it would not change the physics, just the sign we'd get for ER in the end, and the same for cos theta T. Okay, so now what I do, so I've gone through all of that, and what I do now is I have the formulation when I just get rid of the sine theta terms and take all the cos thetas and set them equal to 1. I have the formulation that Griffiths starts with in section 9.3.2, okay? And that is EI is equal to EI e to the I K1 Z minus omega T times X hat. BI is equal to EI over V1 EI K1 Z minus omega T Y hat. And then ER is equal to ER e to the I minus K1 Z minus omega T X hat. BR is equal to minus ER over V1 e to the I minus K1 Z minus omega T Y hat. and then E transmitted looks like E incident because it's a right-hand going wave, only as it's E, the magnitude or the amplitude rather is ET, and the amplitude of the magnetic field is ET over V2. So I've got these now, and what I'm going to do is just apply the boundary conditions, right? But the boundary conditions now are really simple. And so the boundary conditions, the first time we applied the boundary conditions, what that did was told us that the polarization of the incoming wave is the same as the polarization of the reflected and transmitted wave. And that allows us to rewrite these equations in a much simpler form. And then the boundary conditions here are that the electric fields parallel to the boundary are the same on both sides. And that tells me that this term plus this term is equal to that term. And at z equals 0, at z equals 0, I can factor out the e to the minus omega t. And so I'm going to get EI plus ER is equal to E transmitted. And then for the magnetic field, being the parallel component of H being the same on both sides of the boundary tells me that BI over mu1 is going to be BI over mu1 plus BR over mu1 is going to equal BT over mu2. So that matches that boundary condition. And again, the y hats don't matter because they're all in the y hat direction. And I factor out e to the minus I omega t. And then what I get are these really simple boundary conditions. EI plus ER is equal to ET. EI over mu1 V1 minus ER over mu1 V1 equals ET over mu2 V2. I can take this and rewrite it as EI minus ER is equal to beta ET, where beta is equal to mu1 V1 over mu2 V2. And then I can take this boundary condition here, just rewrite it down here, and I take these two equations and add them up, and what I get is ET is equal to 2 EI over 1 plus beta. And I take this equation and subtract it from this equation, and I get ER is equal to 1 minus beta. I take beta times this equation and subtract 1 from the other. And I get ER is equal to 1 minus beta over 1 plus beta times EI. And again, beta is this mu1 V1 over mu2 V2, where these are the speeds in the media and mu's are the susceptibilities of the media, of the media. Okay. So, right. So generally speaking, he says this in the book, mu1 equals mu2. And so in practice, beta is roughly V1 over V2. So I can write down that generally speaking, ER is equal to V2 minus V1 over V2 plus V1 EI. And ET is equal to 2V2 over V1 plus V2 EI. And these look remarkably like things you get when you consider a wave on a string. They look remarkably like the equations you get talking about the speeds, the velocities of two balls that have collided in one dimension, which you get from conservation of momentum. These have the same form. There's a couple of checks here that are kind of reassuring. So if V1 equals V2, and if V1 equals V2, that's the same as saying there's no like material 1 is the same as material 2, and so there is no boundary to speak of. And a couple of checks here is if V1 equals V2, then E transmitted is equal to E incident because nothing happened at the boundary, and E reflected is equal to 0 because nothing happened at the boundary. And if V1 is greater than V2, meaning the wave speed on the left-hand side of the boundary, the incoming side, is faster than the wave speed on the outgoing side, then NR hat is equal to minus NI hat, meaning the reflected wave, the polarization flips on the reflected wave, okay, as opposed to bouncing back the same way. And so, okay, so I'm going to leave it at that for this particular part and then come back. I'm going to say to come back in just a minute, which is kind of silly because you can just listen to these whenever you want.